In the next few videos, we will go over a simple IP and we will see how Cocotb is used in a real world case. So what we are taking over here is a DMA IP, and basically what the DMA IP has are three interfaces, two AXI interfaces which are connected to domain A and domain B, and AXI led configuration interface. And the specification tells us that this particular IP is going to support single transfer and burst mode transfers. And in case of burst mode transfers, the kind of transfers it supports are fixed, linear, and wraparound bursts. And in case of wraparound burst, the burst size at which it will wrap around is again configurable. Then there is support for unaligned address. The data bus can be either 32, 64 or 128 bit wide, and the address bus can be 32 or 64 bit wide. Configuration bus is always going to be 32 bit wide. And the interfaces, as we already said, was two AXI data buses for transferring data from one memory domain to another. And this can be used as either bridge DMA or local DMA, and an AXI light bus for configuration. Then the programming of this DMA, there are two ways in which it could be programmed. One is a single shot mode. So when we speak of single shot mode, basically what is happening is the CPU comes, it programs one transfer, and when the transfer is done, either the CPU gets an interrupt or the CPU is polling the status bit. And when it sees that the transfer is done, it will come and it will program the next transfer. So basically single shot mode, for each transfer, we require the CPU to interact with the IP. There is a second mode which most DMAs support, and that is a packet descriptor linked list mode. So what happens over here is that whenever CPU has a packet to send, it will append that packet to a linked list, and then whenever the DMA has finished transferring the previous packet or is in an idle state, if it sees that a packet has been queued up, then it will go fetch that packet. That is, it will basically process the linked list, fetch whatever is the next node on the linked list, load it into its register, and then do that DMA operation. So here the CPU as well as the DMA can operate independent of each other. The CPU does not need to wait for the previous transfer to complete before queuing up the next transfer. As long as the CPU has a packet to transfer, it can just add it to the tail of the current linked list, and whenever it gets an interrupt from the DMA, or whenever it executes a housekeeping routine, it can always come in, check at what state the DMA is currently, and delete all the nodes from the head of its linked list till that point and shift the head of the linked list to the current node. Okay, so that's the description over here. This is your single shot mode, this is your packet descriptor mode, and here we are describing what the structure of the linked list is. Okay, and then this is followed by the register map description. So basically what is there at each register address. Okay, so we'll be uploading this document to a common location form where you can access it. So we'll just skip through this. And then finally, based on whatever is given till now, we will come up with our verification plan. So our verification plan right now is to use a Cocotb environment, use PyVSC for randomization and coverage capture, use Cocotb RALGen for RAL test, Cocotb constraints for generating register constraints, and simulator we are going to use Icarus, and we are going to use pguardial for dumping out different test bench components. VIP, since we are using AXI, we will be using Cocotb EXT AXI for both AXI and AXIL. Then for doing the register read-write test, we'll be using RALGen. And for accessing individual registers, we'll be using the pguardial Python module. Now the first case that we are going to run is a basic version check. So if you look at our register definition, there is the very first register in our register definition is the version register. So that is this one over here. So this is at address 0, base offset 0, size is 4 bytes. and it contains version min, which is 0, version max, which is 0, and IP ID, which is 1. Okay, so that's the first test that we are going to run. So the way this test will run is that we will reset the DUT, we'll wait for the device to come out of reset, then we'll read the version register, and then we'll check whether whatever we have read matches what we saw up over there. So basically, the min version, max version are 0 and IP ID is 1. Okay. Then there will be a bunch of other tests which we'll have RAL test, we'll have random read write test. We will have to define what our coverage bins are. So on coverage bins, we have a coverage bin for single versus burst mode. And then burst, we will have different burst types. Then single shot versus packet descriptor mode. Then whether this cross between all the source domains A and B, cross between all the destination domains A and B, then cross coverage between source, destination, burst, and packet descriptor modes, and cross coverage between source, destination, single mode, and packet descriptor. Okay, so these are the coverage bins that we are going to target. And once we have written all these tests, what we are basically going to do is we are going to check whether all the targeted coverage bins have been hit or not. Now let us go to our Cocotb environment. Okay, the way we have structured our code is we have a env.py file, and in the env.py file, the important things are this one. So we are using as we said, we are using the Cocotb ext AXI for all our AXI related functions. Then there is an internal library that we have for reset generation. In this case, since the DUT is very small, we are going to generate clock in Python instead of Verilog. Then we are importing triggers. This thing comes from Cocotb. Sorry, this thing comes from pcrdl Python. So what line number 7 does is that pcrdl Python generates a class for whatever register definition you have, and we are importing this class so that we could do register read write using the register names instead of using the addresses. One benefit this gives us is that when during the design phase, the address map can keep on changing, the configuration register space can keep on changing. And if we hard code the addresses, or if we hard code the register fields, then it will become difficult to change the design if we find that there is a more optimal way of doing the same thing. So this helps abstract the uh, individual register fields. Then the Python module basically supports synchronous callbacks, which you can use if you were interfacing your test case directly to an FPGA or silicon. In this case, since we are interfacing it to a simulator, we need to use async await. That's why we are using the async version of this. Now coming to our environment, if you remember in the diagram, we had two address spaces A and B, two memory regions. So we are defining the address space for that. Then the corresponding AXI channels of A channel and B channel. Okay. If we look at the RTL, our prefixes are CXI AXI4, A underscore AXI4, and B underscore AXI4. So those are the exact things that we are using over here. Prefix of AXI4, B AXI4, and CSR AXI4. Once we have defined this, then the next thing what we are going to do is we are going to instantiate this class as a register model. Then we are going to create sparse memory regions for A and B and add those regions to the address space so that we have a target which we can access. Our start function is basically starting two threads, one for reset, one for clock. Okay, and our clock function, we are basically waiting for the reset to be asserted and reset to reach a stage where it is waiting for clock to start. And once we reach that stage, we start generating our clock. Okay, then this is basically a wrapper over the reset end event. And this callbacks which we defined over here, read callback and write callback, we said it is self.readRead and self.writeReg. So we are defining those two down here. So readReg and writeReg, the signature of the function is that it takes an address, width and access width. All three fields are integer. And AXI basically returns bytes. So we are basically reading from AXI. And since it returns bytes, we are converting those bytes to integer. Okay, and on write range again we have the same signature, address, width, access width and data, all are integers. And since AXI takes data as bytes, we are converting it to bytes and then writing it to AXI. Okay, so this is our environment. Next would be our test. So if you look at our description over here, we have a bunch of tests, and if we start putting everything over here in this folder, it's going to start looking messy. Okay, so instead of putting all the tests in this folder, what we are doing is we are creating a tests folder, and inside that I have test A to B. So this is basically testing data going from domain A to domain B. Then test trial, so this is doing read write on every register, and test version, which is basically reading the version string. So we'll take a look at each of the tests. Test version.py. So we are instantiating our environment. We are calling environment start, and then we are awaiting this function. So in this function, what we are doing is we are waiting for reset done. Then reading the fields of this register version register, and then checking whether these fields that we have read has the IP ID 1, version max 0 and version min 0. Okay, so if I want, I could run a single test, or else I can basically run an entire regression. So the next test A to B. This upper signature is the same. So here basically we are calling initialize A to B, and initialize A to B, what we are doing is the packet length we are randomizing between 0 and max length of that channel. Source start address, again we are randomizing such that it fits within the channel. That's why we are doing -env length. Then same with the destination start address. Then we are generating random data. Then whatever data we have generated, we are writing it to the source address space. Then in the register, in the DUT register, there is a field called source address. To that we are writing the start address. Destination address, we are writing the destination address. Then to the length register, we are writing length, and the control register, we are setting the bit 1. So that bit, start bit, we are setting it so that it starts DMA transfer. Okay, so this is your initialize function. Then after initialize is done, we are waiting for some time. So this time is to ensure that if busy does not transition immediately on the next cycle, then we are giving some time for busy to transition. This can happen if the busy is generated in a different clock domain and it is registered in a different clock domain, then there will be some synchronizers sitting over there. After waiting for some number of cycles, then we are polling for the busy status. And as long as busy is not equal to 0, we wait for 100 nanoseconds. So this time, depending on what kind of test we are running, we can increase it. Once we see that busy has gone low, then we are reading data from the destination space, and we are checking whether the data that we have read over here is same as the data that we had set over here on line 31. Okay, so this is A to B check, and then finally we have RAL check. So in RAL check, basically what we are doing is we are using this DMA regRal, and that has a RAL test in it. And from that RAL test, we are currently calling the read write test, ral.read write test. So let's just take a look at that as well. So this file is defining the mask for every register, and then in the read write test it is basically doing a reg.write for every register. So this thing R is basically self.regModel.getAttribute key, where key is the register name. So we are getting that register, then we are doing a write to it, we are doing a read, and then we are checking that whatever we wrote. So not every field in a register will be writable. Some fields will be read only. So whatever we wrote in that, we mask out the read only fields. Okay, that is our write mask. And then whatever we are reading, there when we read it back, there will be some fields which cannot be read. So we are masking those as well on the read value and checking whether whatever we wrote matches whatever we read back. Okay. Now looking at our makefile. On the makefile side, till line number 4 until line number 13, whatever we have. So line number 3 to 13 is standard uh, Cocotb constructs. What we are doing is on line number 14, we are defining the 3 tests that we had in our tests folder. Then we are defining a regression target, and we are saying this regression target has a dependency on the tests target. Okay. And in the tests target, basically, so tests will expand to each one of these. So in the tests target, then we say make sim module equals to test dot whatever test name. So test dot test a to b, test dot test trial, and so on. And then we are saying the result of each of the simulations should go into a separate file. So results dot whatever this test trial, test a to b, whatever that is, it should go into that. Okay, so this is our regression environment. Now if we run make, so test a to b has run. Test trial has completed, and test version check has completed. So if we see over here, we have read this value. So the lower 16 bit is 0, the next 16 bit is 0, and the final bit is 1. Now if we want, we can take a look at the waveforms. Let us see whether we have the waveforms. Okay, we have for A to B. Okay, we did not generate the waveforms. So what we can do is make regressions waves equals to 1, and this will generate the waveforms. Okay, so let us take a look at our waveforms. GTK wave, A to B build, tb.fst, and I'll just pull out a few fields over here. So we are transferring from A to B, so I need to look at AW address. Then B, sorry, AR address. Then on B, AR address. B is right, so AW address on B. And the CSR AW address. So let us do a full zoom. So we see that read from A domain has started, and after some time write to B domain has started. Okay, and if you look over here, we are writing to register 14, 18, 1C and 08. So 08 is basically our status register. So since we just set one field, we first do a read and then a write. So we can look at the AW data as well. So this is where we are setting the start bit. Then these are our addresses. Let us zoom in a bit. So we are saying our addresses are, I think length is E, start address is 8, and address, destination address is 4. So start address is 8 and destination address should be 4. Then the final thing which we'll look at is our regression report. So if we see our regression target, we are calling something called as JUnit to HTML, where we are merging all our results.xml file into a JUnit.xml file. And then we are basically converting this XML to an HTML file. So let's take a look at the HTML file. So these are our 3 tests, and in this case all 3 tests have passed. If required, we can take a look at the details of every individual test. If a test had failed, then it would have printed the seed and failure cause over here. Okay, so this is a brief overview of a working test bench which has a RAL model and is able to do register read write. In the next video, we'll take a look at the next version of this test case where we start doing randomization of different fields in the registers.